This is Laplace transform, and this video is an introduction to these transforms, and we will be using a mixing problem with valved input feeders. So as you can see, we have a valve here, and right now at t equal to 0, valve A is open. Valve A delivers 6 liters per minute of a brine solution containing 0.04 kilograms per liter. At t equal to 10 minutes, valve A is closed and valve B is opened. And valve B delivers 6 liters per minute of a brine solution with concentration 0.02 kilograms per liter. Initially, as you can see here, there are 30 kilograms of salt dissolved in 1,000 liters of water. And the exit valve C, which empties the tank at 6 liters per minute, maintains the contents of the tank. So we have a constant volume inside the tank. So we will assume that the solution is kept well stirred, and what we are going to be doing is determining the amount of salt in the tank at all times. So our goal is to determine the amount of salt, mass of salt in the tank at any time t. Okay? As you can see here, we have x of t, and x of t is the amount of salt in kilograms in the tank at time t. Okay, so we have seen a simpler version of a tank problem in the past, but here we do have a valve that is closing and a valve that is opening after a certain time period. The amount of salt leaving the tank, or the tank's salt content, is depleted at a rate of 6 liters per minute. And then, of course, we have x of t divided by 1,000, and that would be x of t kilograms of salt per 1,000 liters. So that's how we would come up with 3x of t divided by 500, and that would be kilograms per minute. Now, let's talk about the salt that enters the tank. As you can see here, that volume of salt depends on which valve is open. So we will go ahead and call this the salt is enriched at a rate of G of t. And let's go ahead and define G of t. So G of t is equal to 0.04 kilograms per liter, of course multiplied by 6 liters per minute. And we're going to have 0.24 kilograms per minute. And this is from time 0 to 10. And this is, of course, valve A. Okay, let's do the same for valve B. So we have 0.02 kilograms per liter. You can see that right here, times 6 liters per minute. And we have 0.12 kilograms per minute enriching the tank for any time t greater than 10. And that is valve B. Okay, so now how does this x of t change? So x of t changes at a rate. And so here we have the derivative with respect to t. That change in x of t is equal to g of t, what's coming into the tank, minus what's leaving the tank, the amount of salt being depleted. Now we could go ahead and rewrite that as dx dt plus 3 over 500 x is equal to g of t. And we do have an initial condition. See if I can move this over just a bit. With an initial condition, and they did give that right here, and that would be x of 0 is equal to 30. Of course, that would be 30 kilograms. So in order to solve this initial value problem, we would have to use some previous techniques, but we would have to break up these intervals. And so what we want to do is find a more convenient way to solve this IVP. And of course, we have linear constant coefficients equations, and we do have a jump discontinuity at t equal to 10. So we introduce the Laplace transform. And the Laplace transform of a function f of t, so let's just go ahead and write that. On 0 to infinity is this. F of s is defined as the integral from 0 to infinity of e to the negative st multiplied by f of t dt. So we will be multiplying f of t by e to the st, and then we will be integrating with respect to t from 0 to infinity. So this actually takes a function of t and produces a function of s. And this is a much simpler algebraic equation to solve. So let's take a look at this. Here we have the domain or the t domain. And here, let's write what we have when our domain is S. So we will go ahead and take these equations that we have found here previously. So in the t domain, we'll have x prime of t plus 3 over 500 x of t is equal to g of t. And that's what we have right here. For the S domain, we will have S multiplied by x of S, and x of S is the Laplace transform of x of t, and then the transform of x prime of t is simply x of S minus x of 0. Let's go ahead and write that x sub 0 here is equal to 30. And now that S is our domain, we can write this as minus 30 plus 3 over 500. X sub S is equal to G of S. Okay, and G of S is the Laplace transform of G of t. Okay, so now we can find x of S in the S domain without solving any differential equations. So now the solution is x of S is equal to 30 divided by S plus 3 over 500 plus G of S over S plus 3 over 500. So how we solve for, or rather convert from the T domain to the S domain, well, we can use tables, theorems, and many other things that depend on the type of equation that we have. However, we actually have a single formula now for G of S, and that's 0.24 over S minus 0.12 over S e to the negative 10s power. And then the transform of x of t is equal to (30 over S plus 3 over 500 plus 24 over S times S plus 3 over 500 minus 0.12 e to the negative 10s, whoops, I wrote a t, divided by S times S plus 3 over 500. So note, in order to find, oops, I wanted to go ahead and put x of t. So now we have x of t is equal to, and this is using a table. And a little theory, of course. We have x of t is equal to 200 minus 170 e to the negative 3t over 500 minus 100 multiplied by 0 when t is less than or equal to 10, or multiplied by 1 minus e to the negative 3 multiplied by t minus 10 all over 500, and that is when t is greater than or equal to 10. We could use either. I'm just going to go ahead and put less than 10. and greater than or equal to 10. So if we note here, we didn't need to find any derivatives of trial solutions. We didn't need to break up intervals. Or even evaluate constants. With those initial conditions. So the Laplace transform replaces all of these operations. By using basic algebra. And that concludes this video.